Good morning all. Today we start discussing Module 1. Module 1 consists of 3 sections of Chapter 4. First 3 sections 4.1, 4.2, 4.3. So today we discuss 4.1. Extreme values of a function. Values of a function. In this section we have two different definitions and we have two theorems. We omit the proofs of the theorems. Omit the proofs and some methods to find absolute and local extreme values of a function. These are the content of this section. So we start with the definition. The first definition is about absolute maximum and absolute minimum of a function on a domain D. So we start with a function. Let f be a function defined on a domain D. By a domain we mean that a subset of R, in particular the intervals. So the absolute value f has an absolute maximum value on D, the domain D, at a point C, if, of course, this point is C is a point on D, if f of x is always less than or equal to f of c for all values of x, for all x belongs to D. So in order to say that this c is the point of absolute maxima, or this f of c is the maximum value of f on D, we need to get this condition. This is very important. F of x should be less than or equal to f of c for all x belongs to D. Then we can say that this f of c is the absolute maximum value and c is the point of absolute maximum. Next we have another definition that comes under definition 1, absolute minimum value. So the only difference is f has the hypotheses are same. F be a function defined on a domain D. By domain D we mean that a subset of R, or in particular it is an interval. So f has an absolute minimum value on D at a point C if f of x greater than or equal to f of c for all x belongs to D. So this is the condition for getting the absolute minimum value of the function on D. Okay. In this case we say that the c is the point of absolute minimum. Okay, so these are the first definition, absolute maximum and absolute minimum value of a function on D. I hope that you might have seen all these in your +2 classes. Nevertheless, I'll explain these definitions using some functions, some trivial functions or obvious functions you have studied in your +2 classes. So I take this function and consider this point. I assume this is 0 and I take x in this way and f of x in this way. This is our f of x. So this is the graph of y equal to f of x. Because I take f of x in the y-axis. So if you consider the point 0, you can say that if this is our interval or this is our d, and I take this is -1 and this is 1. Okay. If you take this is our d, say closed interval -1 1. So d is our closed interval -1 1. You can say that if you take any x here, any x, then x square, this is the definition of this f of x is x square here, because this is a parabola, it's a common curve. So x square, we can say that x square is always greater than or equal to 0 square, right? Because in this interval, when we take any x and take the square of that, that will be always positive. So this says that 0 square is always less than or equal to x square for all x belongs to d. So this shows that the point x equal to c is the point of absolute minimum, or you can say that this f of 0 is the absolute minimum value of f of x, say f of x equal to x square in d. What is our d? D is -1 1. So this is an example of a absolute minimum. Okay. Similarly, you consider another function. I'll draw the graph of that function. So this is a function. I'll write a function like this. For the simplicity, I take this function f of x as f of x equal to -x square. So I take x in this way and the y-axis f of x in this way. So this is the graph of y equal to f of x, that is equal to -x square. Okay. Now consider the same interval -1 to 1 as the domain D. This is our 1 and this is our interval -1 1 as D. Okay. When you take the same domain D -1 1 and consider the function f of x equal to -x square in D, we can say that 0 square is always greater than or equal to x square -x square for all x belongs to this interval, because -x square is always, this is -1 1. So we can say that -x square is always negative. So if you take any value in this interval or the domain D, we can say that 0 square is always greater than or equal to -x square. Okay, this shows that x equal to 0 for this function f of x equal to -x square is a point of absolute maximum. Okay, the value f of x, f of 0, in this case f of 0 is the absolute maximum value of f over the interval over -1 1. So we can say that this absolute maximum and absolute minimum value of a function depends on the interval and the value of the function in that domain. Okay, so this explains the definition 1. Next we have a theorem, the extreme value theorem. This theorem is known as extreme value theorem. The statement is, if f is continuous on a closed interval AB, then f takes on both an absolute maximum value capital M and an absolute minimum value small m in closed interval AB. That is, there are numbers x1 and x2 in AB itself, closed interval AB itself, with the property that f of x1 is equal to small m and f of x2 equal to capital M, and for every other x in AB we have this inequality, small m less than or equal to f of x less than or equal to capital M. Okay, so this is what we call extreme value theorem. Okay, so this is the definition, sorry, this is the statement of the theorem. We are not bothered about the proof of this, but we need to apply this theorem for solving the problems. So we need to later we will find the methods to evaluate the absolute maximum and absolute minimum using this theorem. Okay, this asserts that if you are considering a closed and bounded interval AB, you can get the absolute maximum value and absolute minimum value in the interval itself. Okay, so the one possible question is to find the points of absolute minima and maxima in an of a function in an domain closed interval AB.